All right, let's jump right into this explainer, where we're going to tackle today's big essential question. How exactly do forces explain changes in motion? Now, if you've ever wondered why a super heavy object suddenly jolts forward, or why something flying through the air eventually, stops, well, you're in the exact right place. We're going to really look closely at the core ideas around forces and interactions. We'll be using some incredibly clear visual models to help us understand those invisible pushes and pulls that literally dictate how everything in our universe moves.
So today we're basically building a toolkit. We are going to cover setting up your system, drawing force diagrams, positive and negative directions, balanced versus unbalanced forces, a real-world example to tie it all together, and then a quick final check and exit.
Okay, part 1, setting up your system. Before we can even begin to figure out how things interact, we have to isolate exactly what we're looking at. Science can get incredibly complicated if we try to calculate, well, everything in the universe all at once, so we really need to narrow our focus. Actually, think of it like drawing a giant imaginary box around the things you care about for your experiment. If we're studying a rolling ball, our system might just be the ball and the floor it rolls on. We intentionally ignore the wind outside, the cars driving by, the whole shebang, because separating the system from the rest of the environment is what allows us to model things clearly and accurately.
And within that carefully chosen system, we look for forces. A force is really just the physical interaction happening between those specific objects we just isolated. Usually, it's just a push or a pull. Whenever you observe a change in an object's motion within your system, say something speeds up, slows down, or changes direction, you are witnessing the direct result of a force at work.
Moving right along to part 2, drawing force diagrams.
Turning these concepts into visual models is surprisingly simple. We just follow 3 quick steps. First, isolate the system. Second, identify what's interacting. And third, draw arrows. Honestly, the arrows are the secret sauce here. The direction the arrow points shows the direction of the push or pull, and the size, like the actual length of the arrow, shows the strength of that force. A massive push gets a super long arrow, and a tiny little tap gets a short one.
Next up, part 3, positive and negative directions. So we have our visual arrows, but to make them mathematically accurate, we have to bring in positive and negative numbers. By standard convention, we assign a positive number to forces pushing right or pushing up. And conversely, we assign a negative number to forces pushing to the left or pushing down. This is an absolute game changer because it lets us translate a simple visual drawing directly into a math equation, which is definitely crucial for our next step.
Which brings us to part 4, balanced versus unbalanced forces.
This right here is the absolute core of understanding why an object's motion actually changes. The motion of any object is determined by the total sum of all the forces acting on it. We call this total sum the net force. You find the net force by just adding up all those positive and negative values we just talked about. If you've got multiple arrows pushing and pulling on an object, the net force is just the final mathematical result when you combine them all together. And here is the crucial point to take away. If you add up all your forces and the total sum is exactly 0, those forces are balanced. When forces are balanced, the object's motion does not change. Period. End of story. However, if that total sum is not 0, whether it's a positive number or a negative number, those forces are unbalanced. And unbalanced forces absolutely guarantee that the object's motion is going to change. It's going to speed up, slow down, or change direction.
Let's put this into practice. Part 5, a real-world worked example.
Let's apply our combined toolkit to a real-world scenario. Okay, imagine this system. A heavy desk is our isolated object. We have 2 interactions happening. Student A is pushing to the right with 20 units of force. Maybe they skipped breakfast today. That's a positive 20. Student B is pushing to the left with 35 units of force. Because it's to the left, we assign it a negative value, making it minus 35. To find the net force, we just add them up.
And this brilliantly illustrates our mathematical model in action. Positive 20 plus negative 35 leaves us with a calculated net force of negative 15. It's great because the numbers just do all the work for us, cutting right through the confusion of the opposing pushes.
So, let's break down what this evidence is actually telling us. Because the sum, negative 15, is not 0, we instantly know these are unbalanced forces. Therefore, the desk's motion is definitely going to change. Furthermore, that negative sign, it isn't just some math quirk, it provides our concrete evidence for the direction. Since negative means left in our model, we can confidently conclude and predict that the desk will be pushed to the left.
Wrapping things up with part 6, final check and exit.
We've successfully built and used our toolkit. You can define a system, draw the forces, crunch the math, and predict the motion. But before we totally wrap up this explainer, let's do a final check to avoid a really common misunderstanding. It's a tricky concept that honestly trips up a lot of people. Think about this. If you see an object already in motion, like, say, a hockey puck sliding across perfectly smooth ice, does that automatically mean there are unbalanced forces currently pushing it just to keep it going? Take a second to think about what our net force rules actually dictate.
The answer is an absolute no. In our universe, if the sum of the forces is 0, the motion simply doesn't change. Now, that doesn't necessarily mean the object has to be completely still. It just means whatever it's currently doing, it keeps doing. So an object that is already moving will just keep coasting steadily at the exact same speed and in the exact same direction as long as the forces remain balanced. It only needs an unbalanced force to change that speed or direction.
So, I'm going to leave you with this final question to ponder on your own. Using everything we've uncovered today about systems, net force, and predicting motion, if a meteor is out there in the deep vacuum of space, already drifting along, and no new gravitational or physical forces interact with it, meaning its net force is a perfect 0, what exactly will happen to its motion 100 or even 1,000,000 years from now? Think about our toolkit, keep asking questions, and keep exploring the amazing physical forces around you.